Okay, guys, I'm having a hard time kind of staying focused today. I know maybe you guys are too. We just spent a lot of time talking about movies and TV shows instead of talking about organic chemistry. But now it's actually time to get back to it. And so I think where we left off was we were still sort of in the section where we were dealing with aromatic compounds, and we haven't quite got to electrophilic aromatic substitution yet, but that's what's coming up next. And so there are some reactions that we need to do when it comes to the reactions of aromatic compounds, and they all happen at the same position in that compound. So we're not really going to learn any reactions on an aromatic ring at the moment. We're going to learn some reactions one space removed from an aromatic ring, and that's called the benzylic position, specifically when we're talking about a six-membered ring. And so what I want to do is I want to get into those reactions, and then we're just going to stop, kind of like hard stop at that. And then we're going to bring in electrophilic aromatic substitution reactions. And we'll stop and we'll pause and we'll talk a little bit more about them at that point. So let's go ahead and get the screen going and see where this leads us for the day. All right, so we talked about how to identify aromatic compounds. We talked about Huckel numbers. We talked about the two criteria to be aromatic: continuous ring of conjugated double bonds, which really just means a continuous ring of unhybridized p orbitals that are planar. And it also had to have a Huckel number of electrons. And so we talked about what that is. And so we spent a lot of time thinking about how to identify aromatic compounds, but we didn't do any reactions of aromatic compounds. And that's what we want to do now. And so there are a couple of reactions. I'd say about, about 3 or 4 of them. And the way that I'm going to introduce it is really, we're going to say that they all happen at the benzylic position. And so recall that allylic is one removed from a double bond, and benzylic means the same thing, except we mean one space removed from a benzene ring. So there's the benzylic position. And so all of the things that we're going to do today will happen at the benzylic position. And so I'm going to start off with oxidation. Then I'm going to move to bromination. And then once you have bromination and you have a bromine at that position, then you can do substitution and elimination. And so let's go with oxidation first. This benzylic position, and let me go ahead and add another carbon here. This benzylic position is easily oxidized with medium strong to strong oxidizing reagents. So good old sodium dichromate. It's going to oxidize this position. And what happens when you oxidize these positions is that you form, and I'm going to actually you form benzoic acid. I think what's important to notice at this point is that there were 2 carbons attached to the benzene ring, and now there's only 1. So it does oxidation But this benzylic position is so reactive that it actually breaks the carbon-carbon bond apart and it forms a carboxylic acid. So this would work if there was an ethyl group there. It would work if there was a methyl group there. It would work if there was an isopropyl group there. But if there's a tertiary butyl group, then there's no reaction. And so at the end of the day, the requirement for this type of reaction is that one of these positions is gotta be a hydrogen. So as long as there is one benzylic hydrogen, you can do this. The other oxidizing agent, and you should be familiar with this one as well, the potassium permanganate, it will also do benzylic bromination, or excuse me, benzylic oxidation in the same exact fashion with the exact same rules, right? As long as there is a benzylic hydrogen, then you're in good shape. You can get this reaction to work. So here's two reactions that you should know. You should put them on the reaction board and add this to your memory. Oxidizing the benzylic position leads to the formation of a carboxylic acid at the benzylic position. We have a name for that molecule. That's benzoic acid. All right, so that takes care of oxidation. So two reactions that yield to the same product for oxidation. Now let's do benzylic bromination. Just like we did with radical bromination, we can do benzylic bromination where we have NBS and heat. N-bromosuccinimide and heat, and we can add a bromine at the benzylic position. Now, it is a radical reaction, so it also needs a benzylic hydrogen. It does not break the carbon-carbon bond, it just adds a bromine there. So this would work if it were just a methyl group. You could have just a methyl group there. That would add the bromine there, no problem. We already discussed what would happen if we had an ethyl group. If it were isopropyl, it would work as well. That's no problem. It just won't work if it's a tertiary butyl group. It's got to have a hydrogen. This is not the best way to draw it here, but I'm going to go with it. Okay, now if we have benzylic bromination, we have a bromine at the benzylic position, and now what we can do is we can do all sorts of substitution and elimination reactions. So it really will depend on the substrate. So there's a primary substrate versus a tertiary substrate. If I were to do a substitution at this position, which one do you think would be most likely to undergo unimolecular substitution, and which one would be most likely to undergo bimolecular substitution? In other words, SN2 versus SN1. Well, remember that SN2 is a concerted mechanism. Both the nucleophilic attack and the loss of the leaving group, they happen at the same time, and so you need an unhindered substrate. And so what you're going to find out is that the SN2 reaction is more favored for the primary substrate, and the SN1 reaction would be more favored at the tertiary substrate. Remember, in an SN1 reaction, it's stepwise, and it involves the formation of an intermediate carbocation. And if I form this cation, it's a benzylic cation. And so one of the things I'd like you guys to remember is that the benzylic cation is even more stable than the allylic cation because of the significant amount of resonance of delocalization that the positive charge can get by delocalizing into the benzene ring. So the same thing is going to happen with E2 and E1. The problem with E2 is that I can't do elimination towards the benzene ring. So I have to do elimination away from the benzene ring. Remember, I can't form another bond here because that would be a violation of the octet rule. So it's not appropriate to look at elimination reactions if you have a methyl, just a methyl group with a bromine attached to it at the benzylic position. You need a few more carbons in order to make double bonds further down the road. So here or here. But in the same case, in both cases, if I'm talking about SN1 or E1, both of these structures lead to an intermediate carbocation and then to the next bit of substitution or elimination that happens. And remember, substitution and elimination is really based on the reagents and the conditions. So am I dealing with a strong base and a weak nucleophile? Well, in that case, then you're going to be promoting elimination reactions. Am I dealing with a strong nucleophile and a weak base? Then in that case, you're promoting SN2 reactions, or excuse me, you're promoting substitution reactions. And then the only other question that I would say that you want to remember from that version is, what if it is secondary substrate? Well, remember that in a secondary substrate, you've got SN2 and SN1 in competition with the elimination reaction as well. And so how could you promote SN1 over SN2? Well, in that case, it's about the solvent, right? So it's the solvent choice sort of helps you decide which one of those mechanisms will be in play. I'm not going to do a whole lot of asking you about what mechanisms are in play for a particular reaction. I just kind of expect you to be able to show me mechanisms and products if I give you a certain situation. And so I'm not really going to spend a lot of time talking about substitution and elimination reactions or which one is which. I'm just going to give you products. I'm just going to give you reactants and expect you to show me products. I'm probably not going to test you on the mechanisms because remember, those mechanisms are really back for Orgo 1. And so I'm going to leave that sort of assessment for Orgo 1. That's really all for the reactions. And so I want to just recap. We did benzylic oxidation. And so benzylic oxidation using a medium to strong oxidizing agent creates benzoic acid as long as there's a benzylic hydrogen. You should know both of those reactions. Then we did benzylic bromination, and that's listed here. Remember, this is going to add a bromine. So that's listed in this top set of reactions. Once you have something on the benzene that you can substitute, then you can move into doing substitution and elimination reactions. Once you have something you can do, you can substitute or eliminate, then you can do those reactions. And that's really the end of it for this particular chapter. And so what I want to do is I want to just pause right there, and I want to see if anybody has any questions or has any thoughts they'd like to add about that. All right, we got a few minutes. And so what I want to do is I want to introduce the next section. The next section is about aromatic substitution reactions. So I think at the end of the day, it took us just about 2 hours over the course of 2 lecture periods to get through all of the conversation about aromatic compounds. What we haven't done is we also did a few reactions. Now we're going to talk about aromatic substitution reactions, and aromatic substitution reactions will probably take 3 times as much time in order to get through all of the information. The reason being is that there's a lot of details that are not easily understood, but there's a lot of details with these reactions that you're capable of understanding with Orgo 1 and this point in Orgo 2's knowledge that you've developed. And so we really can get into a very deep look in the chemistry, and that's what we're going to do. And that's why it takes so much time to get through it all. Now, at the end of the day, there's a lot of mechanisms in this chapter. And so I know maybe you're overwhelmed If you're in Orgo 2, you're feeling at this point, man, I've done a lot of stuff and there's a lot of mechanisms to know. Certainly when it comes to the organization of the course as I'm presenting it, this is where lots of mechanisms start to come into play. And so at the very minimum, we're going to learn 1, 2, 3, 4, 5.5 mechanisms at the minimum. And I say 5.5 because there's really 6 different mechanisms, but 2 of them are quite similar. And so they're not going to be that much different. All right, and so what do we want to get at first? First, the first type of aromatic substitution reaction we're going to talk about is electrophilic aromatic substitution. And this constitutes about 80% of the conversation when it comes to aromatic substitution in general. Electrophilic aromatic substitution will compromise essentially 80% of this section. There are other aromatic substitution reactions and mechanisms that we'll talk about, but at the end of the day, this one is really the most important, or it certainly is the most discussed. And so what do I mean by an electrophilic aromatic substitution reaction? If I take benzene and I react it with Br2 in the presence of iron, then I can get a reaction where I add a bromine on the benzene ring. And it may not be clear at first glance what is actually being substituted. Well, remember that there is a hydrogen here, and that hydrogen is no longer there because there's only going to be 3 atoms connected at any of these positions because it's a conjugated system of double bonds. So they're all sp2 hybridized. You can do that with bromine, and so what we're going to do is we're going to learn bromination, we're going to learn chlorination, we're going to learn nitration, we're going to learn sulfonation, we're going to learn alkylation, and alkylation means adding on an R group, and so I should just call it R. And we're also going to learn acylation, and that means putting on an acyl group. Okay. So these are the reactions that are going to form the backbone of what we're going to learn in electrophilic aromatic substitution. Okay. And so what I want to do, the first thing that I want to do, I guess probably the only thing that I want to do for the rest of this particular lecture, is to introduce this reaction that we talked about to start with, which is this bromination reaction. So if I'm going to do electrophilic bromination, I know that I need to react bromine with iron. And so what I end up with is I get 3 dibromines plus 2 irons, and this is really what forms. It's FeBr3. This is the operating species. And so if I take FeBr3, which looks like this, and I react it with another bromine, then we get a really highly reactive complex. So it looks like this. Oops. So this is the first part of the mechanism. This is what gets things going. We get Fe. You know what? Man, I can't do this right ever. There we go. And so this is the reactive species that sort of starts off the reaction. This will do the substitution reaction that I'm looking for. So benzene's fairly stable, and those double bonds aren't particularly reactive. But if I have the right reactant, then I can get the aromatic system to break. But what happens? This forms an intermediate carbocation. And I hope that you can see that there's quite a bit of resonance in this cation. In fact, these cations are particularly important because of all this resonance. And so it's important to show the reader all of the possible resonance structures of the sigma complex. And this is what this is called. It's called a sigma complex. So what I want to remind the reader, or the viewer, I guess, the student, is that there is still a hydrogen at this position. There is a positive charge here, but that's still a hydrogen. And so this is what we're going to do, is we're going to reform the aromaticity from this FeBr4 minus. So this is what reforms the aromaticity with the bromine now substituted for the hydrogen. And I've got FeBr3 regenerated and ready to react with another Br2 to do the reaction, to continue to do the reaction. Okay, and so what is it? What is one of the things that you have to know? One of the things is that you have to know is that if you react with benzene with Br2 and FeBr3, then you can add a bromine on an aromatic ring. But what else should you know? Well, you have to know this mechanism. Part of the mechanism that you have to know is this step of the mechanism as well, the formation of the reactive Zwitter ion that is what where this electrophilic substitute, this nucleophilic attack happens. So this is a nucleophilic attack in this step. And so we have to have something that is a good electrophile in order to have the aromatic ring do a nucleophilic attack. And so you have to create this electrophile, and that is part of the mechanism. So this creation of the electrophile is part of is part of the mechanism that I need you to know. So it's the formation of the electrophile, which in and of itself is nucleophilic attack. Then another nucleophilic attack to form the sigma complex. And you see the resonance that's going on in the sigma complex. You will often have to show that to the reader. So when you do a mechanism for bromination, chlorination, whatever the case may be, then you have to show all of the sigma complexes as well. And then you have to show the final proton transfer that recreates the aromaticity. And so what I'm going to do is I'm going to leave it there for the day, because that's a good sort of warm up. And we're going to get really seriously involved with a lot more reactions like that. At the end of the day, the chlorination reaction will be very similar. We're going to form an initial electrophile that then the benzene ring will go along and react with. Instead of FeBr3, it's aluminum trichloride, so it's AlCl3, and it's going to form the electrophile essentially in the same way. Then the electrophilic aromatic substitution reaction happens in the same way. It's the same mechanism at its heart, but you are dealing with different reagents each time. So I did say we're going to learn five and a half different mechanisms at the minimum, but what we're really learning is slightly different variations on the same mechanism. And so you should have some confidence in the fact that if you really get the mechanism down in one situation, it shouldn't be that big of a leap to get it down in the next situation as well. And so I'm going to leave it there for the day, and I'll see you guys next time